An interference pattern can be created by the thin air gap between a spherical lens and a flat surface. The light and dark rings are known as Newton's rings, and they can be used to test how spherical a lens is. This is how it's set up, and the spacing of the rings will depend on the radius of curvature, big R, of the lens. That means that the radius of curvature of a lens can be calculated from the fringe pattern. Also, any aberration in the lens will show as unevenness in the fringe spacing. So when it comes to solving problems with thin films, here are the things to consider. You need to know the refractive index of the film and the materials either side of it. Then there are two things that the phase differences will depend on. One is the optical path length through that film, and the other is any possible phase change at the surfaces. You also need to understand that there always, in any situation, the reflected beam plus the transmitted beam have to add up to the incident light. This is simply conservation of energy. And we assume, of course, that these films and these materials aren't absorbing any light. So, if reflection is a maximum, then the amount transmitted must be a minimum, but if the reflection is to be a minimum, then the amount transmitted would have to be a maximum. So let's work through an example. Anti-reflective coatings on cameras and glasses use thin films to ensure that visible wavelengths have minimal reflections. They do this by starting with a wavelength in the middle of the visible spectrum, which is about 500 nanometers. And then they plan the thickness of the film to make destructive interference in the reflected rays. So this, of course, means it makes constructive interference in the transmitted rays, so the transmitted light is at a maximum. Now, there'll be a thickness where the two reflected rays are 180 degrees out of phase. There'll be a greater thickness, of course, where they are 360 plus 180 out of phase, and so on, but we only care about the minimum. Now, our AR coating, it will be sitting here on top of glass. So we've got air, coating, glass. So N is 1, N equals 1.5, and the coating is N equals 1.3. So again, we've got two rays. One bounces off the top of the film that we want, the other bounces off the bottom, and we have a thickness T of the film. So if we set that we want this in the visible, so a middle lambda of 500 nanometers, we want to know the thickness. Now in this case, R1 has reflected off a higher refractive index, but so has R2. So we have zero phase change between the two of them. So the phase difference is due to the path length difference only. So the optical path length difference is 2nt. So since it's to be an anti-reflective coating, we want destructive interference in or between the two reflected rays. And for the case where we've got a higher refractive index underneath, we have the path length difference equals half a wavelength. In other words, 2nt equals m plus a half times lambda. And the minimum thickness is where m equals 0. So we have 2nt equals lambda over 2. T equals lambda over 4n, which is 500 by 10 to the minus 9 over 4 times 1.3, and that is 96 nanometers.